Welcome, everyone. It's good to see you again. How have you been? Okay, everyone, I hope you enjoyed your meal. Today we're going to continue with the review, obviously, with the level gases and thermal physics. All right. The last class, we're applying some formulas for the general level gases. I mean, the level of Charles Boyle Gay-Lussac combined gas. And obviously, we are dependent to solving a few problems with the ideal gas. All right. Today, we're going to apply a couple problems that contain obviously gases, electrons that we're going to provide in combination with the kinetic energy. All right. So if you have some doubts, questions, don't hesitate to let me know. And for that reason, we have two singular problems. Okay. In the first one, we have a cylinder that contains 2 mole of helium gas at 20 Celsius degrees. As soon as the helium behaves like ideal gas. And we have 3 questions. The first one, find the total energy of the system. And the second one will be, what is the average kinetic energy per molecule? The third one, how much energy will have to be added to the system to double the RMSA? Remember the radical medium speed, right? That's supposed to be the velocity of the gas in one singular space. And remember, the problem gave us already what will be the molar mass of the helium. That's supposed to be equal 4 times 10 and the negative third power kilograms per mole. Okay. What we have to do in this situation? Well, just like that, in every problems for your students, the first thing that we have to do is analyze the data. For example, in the data, we have the quantity of mole. Okay, this quantity of mole that's supposed to be 2 moles. All right, and we have the temperature. The temperature will be 20 Celsius degrees. But remember, every time they're going to working with the level gases, this temperature that must to change in the Kelvin degrees. Okay, so in the question, we have 3 questions. The first one, we're going to trying to looking for what will be the internal energy of the system. Remember, the energy of this gas is a monatomic gas, the helium. After that, they're asking for the average kinetic energy. I mean, one had mass, velocity, second power. This is the average kinetic energy. If you remember, this average kinetic energy is equal to 3 times, 3.5 times Boltzmann constant times the temperature. And after that, how much energy? You're asking for the new increase or delta U. I mean the new increase of kinetic energy or internal energy in this case. Okay, what we're going to do? Step number 1 is the easier part of them because they're asking for the total internal energy of the system. Because the helium, my dear students, um, is an is a monatomic gas, we can apply the following singular equation. U equals, or internal energy equals 3.5 and RT. Testing, can you hear my voice, guys?
Yes, mister.
All right then. So what we're going to do, we're going to replace those values. For example, the letter N, remember, represents the quantity of moles that we have in this problem. We have 2 moles. The capital R value is the ideal constant of the gas. That will be 8.314 joules per mole Kelvin degrees. All right. And the temperature we have 20 Celsius degrees, but remember, we cannot work in using Celsius degrees. If you really want to change Celsius degrees into Kelvin degrees, the only thing that we have to do is add in 273 degrees plus 20. In this case, we have 293, okay? 293 Kelvin degrees. If you see, obviously this number 2 can be canceled with this number 2. The quantity of mole can be canceled with mole and Kelvin degrees with Kelvin degrees. And we just can multiply 3 times 8.314 and also by 293. Okay, so in this case, we have 3 times 8.314 multiplied by 293. So the internal energy will be 7,308, 7,308 0.01 joules. This is going to be the first answer. Why? Because we're talking about the helium is a monatomic gas. Questions? Or everything is clear to this far? ¿Está todo claro? ¿O no?
Mister, one question.
Yep.
Where did you get the 8.314 joule?
It's the universal constant of gases. I don't give us that value in the last class, remember? In the last class, I gave it to provide 2 values. One of them using the physics terms that with a constant value of 8.314 joules per mole Kelvin degrees. Or there's another unit using chemistry that will be 0.0821 atmosphere liters per mole Kelvin. Sounds kind of familiar, that one, in chemistry?
Yeah.
Okay, so that's why we have the universal constant of gases. But obviously reasons, we're going to use joules because we are not working with atmospheres at the moment. We're going to looking for energy. Understood? Remember, the capital R value are the universal constant of gases. 8.314 joules per mole Kelvin degrees or 0.0821 atmosphere liters per mole Kelvin. But obviously we want to use the first one. Now, the second question is, what is the average kinetic energy per molecule? The average kinetic energy. This is an interesting question because just to explain you already, the kinetic energy, the average kinetic energy obviously could be equal 1/2 mass velocity at the second power or average velocity at the second power. Okay, but at the same time, this kinetic energy could be given by 3/2 the Boltzmann constant times the temperature. What formula we're going to use? For obviously reasons, we can use the third proportion because we know that Boltzmann constant is a given value, and I told you already in the last class, and T represents the temperature. For that reason, the average kinetic energy in this case will be equal 3.5. The Boltzmann constant, that's why I wrote this over here, will be 1.38. 1.38 times 10 at the negative 23 power joules per Kelvin. Joules per Kelvin. And this value will be multiplied by the temperature, obviously, will be 293 Kelvin degrees. Okay, so we're going to solve that equation. Remember, if you have doubts or questions, don't hesitate to let me know, all right? So 1.28 times 10 to the negative 23 power, multiplying by 293, and the answer will be 6.07, 6.07 times 10 at the negative 21 power joules. And this is going to be the second answer. Why we are not using the formula, regular kinetic energy formula? Because we don't know the mass. We don't know the mass, neither we don't know the velocity. So for that reason, we have a serious problem trying to looking for or trying to calculate in that situation. That's why in simple merely words, that proportion can be used to calculate the change of energy or the quantity of energy we're supposed to add to the system. Okay. Or I mean the average kinetic energy per molecule. Now, in the another one says how much energy will have to be added to the system to double the square median speed. Okay. Remember this, the velocity, the square median speed is given like a square root of 3 times the universal constant of gases, temperature divided by the molecular mass or the molar mass, according to the situation. But what is the thing or the serious thing in that kind of, in the problem number 3? And the letter C, in the letter C, remember the change of internal energy will be given by the final internal energy subtracting the initial internal energy. This is a real question. This is not any doubts for that reason, okay? And at the same time, you know, the change of internal energy, because we're talking about the helium is a monatomic gas. Remember, we have this formula, 3.5, and capital R TF minus, same happens over here, 3 times 3.5 and R multiplied by TO. We know all values, but we have one singular problem. We don't know what will be the final temperature. We have to looking for the final temperature. And if you want to replace, or if you want to summarize this formula, we can take the common factor over here. The common factor over here, that will be obviously 3.5 and R. And this expression can be multiplied by TF minus TO. If we really have to know what is the final temperature, we won't have any problems, any situations, okay? But we have a singular problem. The singular problem in this case is we don't know what is the final temperature, but we can calculate that one. How we can do that? Because the problem mentioned the quantity of energy that we're supposed to add the system to double the speed, but we don't know what is the value of the speed. So what I have to do in this case, first step, we have to try to find out what could be the initial square root, the square median speed in that situation. I mean, I'm going to use that formula over here. I don't know if you can see that part of the whiteboard. Okay, velocity square median speed, that will be given by the square root of, I'm going to replace those values. I mean, 3 times, remember the value from the R is 8.314. You know, the units, I'm going to avoid the unit just for space. And the period, the temperature will be 293. And this equation will be divided by the molar mass. The molecular mass, or the molar mass given for the problem, that will be a 4 times 10 at the negative third power kilo. Well, going to avoid the units. So the square root median speed, the root median speed, in this case, I mean the original, will be given by 3 times 8.314 times 293. And this results divided by 4 times 10 and the negative third power, taking square root. So the original speed will be given by 351.67 meters per second. This could be the initial velocity, okay? The initial velocity. Well, at the moment, we're going to use the temperature 290 Kelvin degrees. And you're going to ask, what, Mister, why it's so important to know the root mean speed in that situation? Simple, because the problem mentioned, we're going to double that speed. If I double that speed, I'm going to have another value of the temperature, okay? So I'm going to use that same formula once again, but instead to use 1,351.67, I'm going to double this speed to try to looking for what will be how to say that, the new temperature. So I'll do it over here. Instead to write 1,351.67, once again, I'm going to multiply by 2. 1,351.67. Once again, because the problem mentioned, I'm going to double the speed. Will be 703.34 meters per second. And this equation, or this new speed, will be equal to a square root of what? The entire values. Obviously avoided that time because we don't know the time, the temperature. That will be given by 3 times 8.314 joules per mole Kelvin degrees, okay? We don't know the temperature. We're going to say final temperature, the new temperature, divided by the how to say that, the molecular mass. And the molecular mass, that's supposed to be 4 times 10 at the negative third power kilograms per mole. Okay, what we have to do, well, we can try to simplify that expression. We have 3 times 8.314. Okay, and this result divided by 4 times 10 to the negative third power. And this result will be 2,703.34 meters per second equals to the square root of what? The square root of, in this case, would be 6,235.5. If you see, the mole can be canceled with mole. Mole can be canceled with mole. And joules, another way of saying joules, remember, it's kilograms per meter square, second square. And because we have kilograms, we cancel kilograms with kilograms, and that will be meter square per second square, obviously divided by the Kelvin degrees. And this is going to be the final temperature. This letter K represents Kelvin degrees, okay? Well, what I have to do, simple.
Yes, sir. Can you move the whiteboard, the camera a little bit to
Oh,
the
yeah,
right?
yeah. Thank you for letting me know. Estaba tan emocionado que. Okay, just once again, I'm multiplying 3 by this number divided by 4 times 10 to the negative third power. The answer gave us meter squared second square over Kelvin degrees. Why? Because mole can be canceled with mole. We cannot cancel Kelvin degrees. That's why it's divided. But joules, remember another way to represent joules is the product between the mass velocity square. I mean, kilograms, meter square, second square. And because we have the kilograms located over here, can be canceled with that one, and we have this section. Okay? So what will be the next step? We can take the square root of this number. Okay? Just for simplify the expression. The square of this number will be, I'm going to copy once again, 2,703.34 meters per second equals, the square root of that value will be 78.97 meters per second. This quantity multiplied by final temperature over Kelvin degrees. Okay, just taking outside this square root, this quantity. Okay, and because this quantity is multiplying, when passes to divide, if you see the units, meters per second will cancel, right? And we got 2,703.34 divided by 78.97, and we got 34.23 equal square root final temperature over Kelvin degrees. This is not a number, this is a unit, Kelvin degrees. Remember, we have to looking for the final temperature. What will be the next step to eliminate the square root of any numbers? We have to elevate at the second power both sides of the equation, and we can eliminate that square root, right? So we got 34.23 at the second power. The temperature will be 1,171.69. And if you see, I don't know if you can see this Kelvin degrees is divided, passes to multiplying, and we got the units Kelvin degrees. And we have the final temperature. Okay. On to continue solving the problem to finish the letter C. Did you understand what this for? Well, I'm going to take it like a yes. All right. Well, what we're going to do? Simple. Now it's time to replace in the purple formula and finish the exercise number 3. I mean, the change of energy will be given by 3.5. The number of moles, you know, there will be 2 moles. The universal constant of gases, 8.314 joules per mole Kelvin degrees. And now the difference of the temperatures. I mean, 1,171.69 negative 293 Kelvin degrees. Because both are Kelvin degrees. And if you see, Kelvin degrees can be canceled with Kelvin degrees. Mole can be canceled with mole. And even though this number 2 can be canceled with the first number 2, and the only thing that we have to do is multiply. Okay. The change of energy will be given by 3 parentheses, 8.314 parentheses, 1,171.69 minus 293 close parentheses, and the answer will be 21,916.29 joules. And that's it. That's all that we have to do in the problem. Actually, the problem, the letter A, the letter B, this is not big complicated. The letter A and B. But however, in the letter C is starting to a little bit complicated because we don't know what is the final temperature. So to try to looking for what will be the final temperature, we have to create that full process. All right. That's why we have the extension of the problem. And so guys, questions or everything is clear? ¿Está todo claro, todo azul? Bueno, ahí le tomé una fotito. Le tomé una fotito al problema para que lo tengan ahí en el grupo. When you finish to copy that one, let me know to erase the whiteboard and solve the problem number 2. ¿Ya vieron la ley de los gases con mi hija Velar o todavía no?
Estamos viendo.
Ah, bueno. Entonces ya ven, es un complemento de lo que vieron conmigo. Solo que esta partecita que yo estoy enseñando, eso no se mira en química. En química solo se ve la ley de Charles, Boyle, Lusac. Creo que se mira inclusive de estequiometría. Que si no lo miran ahorita, lo van a ver a principios del segundo parcial. Pero a diferencia de la química, que en la ley de los gases aquí incluye movimiento. Y en química no, solamente cálculo de volúmenes y temperaturas, presión y cosas así. Por eso dudo mucho que usen estas fórmulas en química. Pero en físico sí. Okay, may I erase the whiteboard?
Yes, mister.
Okay, then excellent. All right. I'm going to obtain the space over here. All right. Chon, 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 chon. Okay. Let's going to read the problem number 2. I don't know if you can see perfectly well. Can you read perfectly well the problem, or you need to approach this a little bit more than that in the whiteboard? Or you can read that problem. Can you read the problem?
Yes, mister.
Yes.
All right then. So in the problem number 2 is mentioned a beam of electron moving to east, I mean to the right side, impacts a target in a vacuum chamber. Okay. If 1.25 times 10 at the 14 power electrons traveling at a speed of 3 times 10 to the 7 power meters per second strike the target during each brief pulse lasting 5 times 10 to the negative 8 power seconds. Interesting. What is the average force exerted on the target during the pulse? Assume the all electrons penetrate the target and are absorbed. Penetrate the target and are absorbed. Interesting. And the second one asking for what will be the average pressure? What will be the average pressure exerted on the beam spot, as I'm speaking, okay? And this average pressure exerted on the beam spot, sorry, on the beam spot, okay? On the beam spot, which has a radius of 4 millimeters. And the problem mentioned, we're supposed to have a note. The specific beam spot is the region the target struck by the beam. The struck, that means that there's not gonna be a rebound at the moment of the impact. So this is the meaning of that situation. Okay, so This is the reason why I love physics, because when you study physics is the first year and you have the knowledge with a lot of topics, there's no inconvenience for you at the moment you're going to start to solving this kind of problems. Okay, so if we read the problem carefully, yeah, this is a part of thermal physics. It's going to be a friction, there's going to be a change of temperature. All right, this is a reasonable doubt. Okay. However, in, in this case, we have to apply some knowledge. If you see, moving to the X to the east and impacts a target, there's gonna be a collision. And after the target, the problem mentioned this target is during each pulse, during like 5 times 10 the negative 8 power seconds, and this the all electrons penetrate the target and absorb. Oh, all the electrons. What does that mean? Okay, first of all, we have to establish the data. Remember, we have the total quantity number of electrons. That will be 1.25 times 10 at the 14 power electrons. We have the initial velocity. The initial velocity, this vector, these electrons moving, initial speed of 3 times 10 at the 7 power meters per second will be positive because this is moving to the east. What will be the final velocity? Well, my dear students, the final velocity in this situation will be 0 because at the moment we have the impact, this region struck the beam by the beam, so either the electrons will be absorbed. In that reason, there's not going to be going to come to rest. That's why in that situation. Okay, after that we have the period of time. The period of time for the problem is 5 times 10 at the negative 8 power seconds. And also we have a radius 4 millimeters or 4 times 10 and the third power meters, because remember the radius is supposed to be given in meters. And what else? Additional data. I don't know if you know that already. Well, you studied that in physics, in chemistry, sorry, protons, electrons, and neutrons, right? And the mass of the electron. But if you don't do that, if you didn't know that, is a constant value of 9.11 times 10 at the negative 31 kilograms. All right. This is going to be the data, the full data of the problem. What will be the next step? We have a collision. All right. So we're going to try to calculate what will be the change of the impulse. This change of impulse that will be given by the product between the mass and subtracting the final velocity minus the initial velocity. You remember just like at the old times, right? So what will be the mass of the electrons? Well, the mass of these electrons for one singular electron will be 9.11 times 10 at the negative 31 kilograms. Okay? We'll multiply by what will be the final velocity? 0. What will be the initial velocity? Well, the initial velocity, if you see, is 3 times 10 at the 7 power meters per second. Okay? And this is going to be the impulse. The impulse. So 1.11 elevated at the negative 31 power multiplied by 0 minus 3 times 10 to the 7 power. The answer will be given by negative 2.733 times 10 at the negative 23 power. In this case, remember, could be newtons per second. Newtons seconds. All right. This could be the change of the impulse, but we have a situation. This change of impulse will be useful if and only if we're talking about one singular electron, only one. But how many electrons do we have on this problem? We have 1.25 times 10 of the 14 power electrons. So I'm going to try to looking for what will be the total change of the impulse. This total change of the impulse, I'm going to multiply 1.25 times 10 at the 14 power electrons multiplied by this impulse. That will be negative 2.733 times 10 at the negative 23 Newton seconds divided by the one electron for every electron that we have. Okay? So this answer multiplied by 1.25 is 10, 14, but oh, sorry, 1.25 and 10 the 14th power multiplying by negative 2.733 times 10 and the negative 23, close parentheses, and the answer of the change of impulse will be given by negative 3.42 times 10 at the negative 9 power Newton second. This is going to be the total impulse that I'm looking for. But the problem they are asking for what will be or what could be the the force, the average force. Okay, so remember the situation. The change of impulse or impulse, what will be equal is the product between the average force multiplied by the period of time. If this period of time is multiplying passes to divide, so the change of impulse will over the period of time that will provided by this average force. Okay. So what we have to do, we're going to replace those values. Change of impulse, you know, is negative 3.42 times 10 of the negative 9 power newtons seconds divided by what? The period of time. This period of time will be 5 times 10 at the negative 8 power seconds. And what will be equal? Well, this force might use it because of the moment of the impact, obviously the particle comes to rest, but we're going to have a reaction force. To stop this equal, this force will be negative because we're talking about the friction force. So I'm going to add the negative sign because we're talking about this force will be located against the movement, okay? That's why I'm adding this negative symbol or negative sign, okay? So the answer will be 3.42 times 10 and the negative 9 power divided by 5 times 10 and the negative 8 power. So the force will be given by 0.0684 newtons equals force. And that's it. This is going to be the letter A. Why positive? Because negative times negative gave us a positive value. This is the letter A. Questions?
Mister, can you explain once again why did you put the negative sign in the force?
Because it's the friction force. Remember the moment of the impact, the quantity of electrons comes to rest. Okay, and because it comes to rest, obviously the force is supposed to be located in opposite side of the movement. And remember the second level of motion, the force will be negative if and only if that will be against the movement. And the name of the force who's acting against the movement is the friction force. That's why we are adding the negative sign in the letter F. Understood?
Yes, mister.
All right then. Well, that was the complicated part in the letter A. Okay. Now we have to solve the letter B. The letter B asking for the, what are you asking for? The average pressure. Any idea how to calculate the pressure? What do you think? What we have to do in this case to calculate the pressure?
Calculate the area of the tangent and then force divided by area.
Exactly. We have to apply the Pascal principles or the definition of stress. You have the right answer because pressure, as soon as you can see, pressure is the quotient between the applying force divided by unit from area. So pressure will be given by force 0.0684 newtons. And the area, obviously, resistance will be the area of the circle, right? That will be pi square radius. And the radius is 4 times 10 at the negative third power meters, elevated at the second power. And in that situation, we can calculate the average pressure or the stress, if you wish to call it in that way. So will be, let me calculate the area, pi 4 times 10 the negative third power, second power, okay, divided by 0.0684, which is the reciprocal value, and the answer will be 1,360 0.77 pascals. And this is going to be the pressure, the force and pressure. And that's it. That's all that we have to do in this second problem. Chon, 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 chon. ¡Ya! Y terminamos. ¡Yay! ¿Preguntas? ¿Ah? ¿Todo claro? ¿Todo azul? Y pucha de lo bueno. Uy, qué raro. Pensé que les había mandado esto ya. Y les mandé 2 veces la misma captura, permítanme. Se supone que estoy dando el print screen. Quiero mandarles esto. Vamos a ver. Ahora sí. Ahí se fue. Bueno, entonces mis estimados aprendices, más bien hasta nos pasamos 4 minutitos. No los voy a demorar más. Muchísimas gracias por su atención. Hoy, si Dios lo permite, voy a revisar los 2 classworks. Bueno, el de math, sí, lo voy a revisar hoy. Los 2 classworks y ya para mañana pues ya van a tener el resultado. Así que mis estimados, cuídense, pásenlo bien, tengan una feliz y hermosa tarde. Cuídense.
Gracias, mister. Igual.
Gracias, mister.
Cuídense. Bye bye.
Mister,
Ajá.
yo tengo una pregunta con el classwork que es
Ajá.
para hoy.
Dele, permítanme. Vamos a habilitar para que pueda participar, para que pueda compartir pantalla. ¿Cuál es la duda que tiene?
Espérame. Déjeme buscar. Yo tengo una pregunta con la 2.
Ajá. Permítanme, pues déjenme buscar. Bueno,
No, si quiere le comparto pantalla aquí.
sí, eso sale más barato, eso le iba a decir. Vamos a ver. La 2. Ajá.
Yo ya la saqué, ya hice la gráfica y todo.
Ujú,
Pero cuando me salen los vértices,
ujú.
solamente puedo incluir el punto en el que se unen, o sea,
Sí, en ese es uno. Así es.
ajá, y de ahí me salen, o sea, no me sale ninguno porque no es un área cerrada.
Ah, bueno, entonces si no le salen, o como le digo, los que incluyen dentro del área, dentro de lo que es el área. Si solo hay uno, es uno. Pero dicen, find all the vertices. Si hay uno, pues hay uno. Si hay dos, hay dos. Si hay tres, hay tres. No necesariamente tiene que haber más de uno.
Ok, entonces solamente tendría que poner como solution set y ese único punto y it's not bounded, ¿verdad?
Correcto. Y me imagino de que y que pintó la área sombreada, ¿verdad? Acuerde que eso hay que pintarlo.
Sí, 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 sí lo pinté.
Bueno, perfecto. ¿Alguna otra preguntita que tengan aparte de eso?
No, no sé.
Yo tengo una mister, pero no del
A ver.
trabajo de ahorita.
Ajá. Cuenta.
En la semana morsánica,
¿Sí? Te escucho.
yo estaba fuera de mi casa desde el domingo
Ujú.
y usted me dio una tarea para el martes, creo, si no me equivoco.
Sí, porque originalmente la tarea no era para la semana morazánica, la tarea
Era
era
para el
originalmente,
viernes.
era para el viernes antes de la semana morazánica.
Sí, correcto.
Entonces se me corrió un poco porque debido a que muchos de ustedes, o sea, pero no hablo de 11 grado, sino que en grados en particular, ese día tuvieron bastantes problemas de energía eléctrica, entonces se pospuso
Mm,
para el martes
correcto.
de la semana
Y
morazánica. Ujú.
yo el miércoles regresé a mi casa y la quería entregar, aunque sea tarde, por lo menos para poder entregarla, pero ya no me salía la tarea en el box y no, tampoco me sale en no entregadas ni en entregadas tarde. No sé si la quitó o algo por el estilo, pero no me sale.
Permítame, ahorita le voy a contestar la pregunta. Déjeme checar. Me está hablando de qué clase de física, perdón,
De álgebra.
de álgebra. Ok,
Sí.
permítame. Ahorita le vamos a aclarar la duda. Vamos a ver. La tarea número ¿qué? La 2, ¿verdad?
Sí, la dos.
No sé, aquí aparece, ya le voy a mostrar. Permítame. Aquí lo doy share screen. Mire, aquí aparece más bien la tarea número 2. Aquí, según esto, déjenme ver. Según esto acá, en la tarea 2, solo tengo a Marcela pendiente. Solo a
O sea,
Marcela tengo pendiente.
entonces,
Eh,
creo que, ¿será que yo lo habría mandado desde el viernes?
sí, David Morales, ¿no? Sí, aquí está,
Sí.
¿eh? Ahí está, 70,
Ah.
dice aquí. Aquí ya lo tenía.
Y, y otra cosa, ¿viste? La tarea de ayer,
Mm,
lo mandé como a las 4:50, pero la computadora empezó a
ujú.
decir que estaba sending y sending y estaba la ahorita cargando y cargando y cargando y nunca se mandó. Y se hicieron las 5 y como 2 y 3 y al final se mandó, pero cuando se mandó ya me decía que el archivo este se había cerrado porque usted
Ok,
había puesto que se
vamos a
cerrara.
hacer una cosa. Permítame. Deme un chancecito Estamos hablando de physics, ¿no?
No, de la tarea sí, perdón, de physics,
Sí,
sí,
de physics. Por eso le digo, de ayer physics. Ay, qué bruto, estoy buscando. Ay, mira que lo voy a encontrar en... Vamos a ver.
Y se lo terminé
Ers-
mandando hoy en la mañana, se lo puse, pero eh, Salvador me dijo que se podía poner como en añadir archivos, en vez de como meterlo a tarea, solo, ¿se lo puedo volver a mandar ahorita?
Sí, pero es que eso es lo que estoy haciendo ahorita. Mire, se lo estoy habilitando, ya queda abierto para que me lo mande aquí.
Mister,
Ahorita se lo
yo
mando,
también
mister, gracias.
tuve el
Ujú.
mismo problema que David con
Bueno,
la tarea de ayer.
no hay problema. Mire, yo ya lo estoy habilitando para que lo mande aquí. Ya lo
Ah, ok.
tienen hecho, ¿no?
Sí,
Sí,
sí.
Bueno, solamente para que me lo manden aquí. Ya estuvo, ya está
Ahorita
habilitado.
mismo se lo voy a mandar.
Dale pues.
ok.
Gracias,
Bueno,
mister.
chequen muchachos. Bendiciones.
Cuídense.
Bye
Gracias,
igual.
Mister.
Bye. Bye.
Ok.